Welcome to the debate. If you're flying a single propeller airplane and you try to steer right, the laws of physics don't just pull you right. They try to force your nose straight up into the sky, which is super disorienting the first time it happens.
Oh, absolutely. It's this bizarre phenomenon called gyroscopic precession.
And it's exactly why engineers have this, love-hate relationship with spinning masses. Today we're diving into Dr. Chandan Chattoraj ME503 lecture notes to ask a big question. Are gyroscopic couples fundamentally a stabilizing mechanism that engineers should harness?
Or a parasitic force they must minimize.
I'll be arguing that harnessing gyroscopic stability using theoretical principles is actually essential. We need it for things like spacecraft orientation and naval ship stability.
Ruins handling. Real-world engineering means you have to minimize it to improve agility and, well, reduce component stress.
Let's start with that airplane. A spinning propeller has, massive angular momentum, right?
Right. The whole H equals mk squared omega formula.
Exactly. When the plane turns, it forces that spinning axis to tilt. Physics dictates that this generates a gyroscopic couple, a reactive torque. But isn't the absolute predictability of that reaction a massive asset? I mean, we know exactly how it will behave.
Predictable, yes, but think about why it behaves that way. It comes down to the 90-degree rule of gyroscopes.
Right, where the force shifts.
Yeah, when you apply a force to tilt a spinning object, the reaction doesn't happen where you pushed it. It manifests 90 degrees further along the rotation. So steering right translates into pitching up. For a pilot, you're now fighting the engine's inertia just to make a simple horizontal turn. It's a permanent control hurdle.
It's kind of like trying to walk a giant hyperactive dog. You pull the leash to the right and the dog bolts straight up in the air.
That is a perfect analogy. You see, in textbook theory, you get this elegant, torque-free precession where everything balances perfectly. But in the real world, you are forcing that torque, and the vehicle physically fights back.
Sure, but that fight is exactly what keeps naval ships upright in a storm.
Oh, here we go.
Hear me out. If we scale this up from a little propeller to a massive steel rotor inside a ship, we use that exact reactive torque to counter violent rolling from waves. You're pitting the ocean against the rotor's inertia, and the rotor wins.
It wins the roll, sure, but at what cost to the rest of the ship? Think about steering, or yawing.
Okay.
When a ship with a clockwise rotor turns left, that active couple forcefully shifts the momentum vector. And because of that same 90-degree rule, the reactive couple violently raises the bow and lowers the stern.
Which causes pitching.
Right. You cure the roll, but you induce a severe pitching problem every single time you touch the rudder.
But we don't just let the ship snap in half. Engineers model that pitching as simple harmonic motion. We calculate those forces and design the hull and specifically the rotor bearings to handle the resulting stress.
Modeling it on a whiteboard is fine, but living with it is a structural nightmare. When you force precession on an industrial-scale rotor, that gyroscopic couple acts like a giant pry bar against the bearings.
It is a lot of force, I'll admit that.
A massive, continuous amount. Every time the ship turns or pitches, that pry bar is just grinding the metal down. The metal fatigue is relentless.
Okay, well, if the pry bar effect is so destructive, why do we rely on it for something as vulnerable as a motorcycle? If you're listening to this and wondering why a bike doesn't just fall over, it's because those spinning wheels act as gyroscopes. Doesn't that prove the effect is fundamental to handling?
For static balance in a straight line, sure, but cornering is a completely different beast.
How so?
The math dictates that this force scales exponentially the further the mass is pushed away from the center of the wheel. The higher the tangential speed of that outer mass, the more violently the gyroscope resists turning.
Which explains why engineers spend millions trying to shave mere grams off of wheel rims.
Precisely. If you want a motorcycle to actually be agile, you have to actively strip away rotating mass. Just pulling the inner tubes out of the tires can save up to 2 kilograms right at the outer edge of the wheel.
Wow, that's a huge difference.
It really is. It drastically reduces the gyroscopic drag and lets the bike actually dive into corners instead of fighting the rider.
It always comes back to that tension, doesn't it?
On one hand, leveraging the theoretical mechanics of angular momentum gives us the bedrock of stability for spacecraft and naval vessels.
Right. And on the other hand, the practical reality of dynamic movement means engineers must fiercely minimize that inertial momentum to save their bearings and maintain handling.
It's a brilliant engineering paradox, and we owe a big thanks to Dr. Chandan Chattoraj for sharing the ME 503 lecture notes that sparked today's discussion.
Definitely. There's a lot more to unpack in those notes for anyone looking to dig deeper into the physics.
We'll leave it to you to decide which philosophy drives your design. Next time you see a massive spinning top perfectly balanced on a table, ask yourself, is it a marvel of stability or is it just waiting for a chance to fight back?